In this video, we're going to look at what space-time is mathematically. This is the mathematical foundations to be able to study general relativity from a very rigorous point of view, from a mathematical point of view. So in order to understand space-time, you need to understand what a manifold is, because space-time is a manifold. In order to understand manifolds, you need to know what a topology is. Let's start there. Let's start by building the foundations and moving towards space-time. So here's a very, very simple example of a manifold, which is rather abstract. So a manifold is a set of points. I have represented it as a circle right here. And a manifold has a topological space, which is endowed on it. And this topological space, it's a topology comprised of open sets. So it's important to know what a topology is. And when I say topology, I'm going to try to explain it from the vantage point of general topology, not something like geometrical, but the foundations of it. So a topology is a set. A topology is a subset, a collection of elements. It's a subset of a bigger set. And T, a strip T, and is comprised of it's the subset of the power set. So imagine your parent set is the set M, which is what our manifold is, and what a T is a subset of the power set. So it's a collection of elements, and those elements are sets themselves, which behave a certain way. So the way they behave is that first, the empty set has to be part of the topology. And the second, the set M itself, the parent set of M itself has to be part of the topology. And something that's really important is that imagine you have two sets, you and we, and their intersections, a finite intersections, the resulting set has to be part of the topology. And lastly, infinite unions, arbitrary unions, it has to have the resulting set has to be also part of the topology. So whenever you have a collection of elements T, which behave in this way, have these three properties, it's called a topology. It's called, if you consider the set M and the T, and set T together, it's called a topological space. And topology is used to study continuity using open sets without using a metric. So the topology, understanding topology is important, and I recommend James Moncrief's book on general topology, and that will help you to understand algebraic topology, where you need a little bit of group theory. So let's now look at what makes a manifold a manifold. Besides having a topological space defined, topology defined on it, what makes a manifold unique is that consider an open set in of the manifold. You take a point P, what you could generate is a mapping to R2 in this example. And this mapping takes an element of U and maps it to an element, a subset of R2, to Euclidean space. So when you look at the manifold itself, when you look at locally around a point, it looks Euclidean. You can map it to some Rn, where n is the dimension of the manifold. So there's a mapping that's part of the manifold. And this mapping takes a set U and it has an image point, which is going to be it's going to be the function P of U P, which is a subset of R2. So what is two? In this kind of example, two is a dimension. So this is an example of a two-dimensional manifold. So space-time, for example, is a four-dimensional manifold. So whatever the n is in this example, whatever n is the dimension of a manifold. That's how it's defined. So this is an example of a two-dimensional manifold. So consider you have another open set which is overlapping. The great thing about, manifolds is that you can make transitions and go from one chart to another. So imagine you have a chart defined. So this is, by the way, called a chart, and a collection of charts called an atlas. So this is a chart, for example, for point V. which maps to R2. Then you also have point P, which is another chart. So you have two charts defined there. And you can see that in these charts, there is an overlap. The sets V and the sets exist in both of them. As you can see, the point V and P, they both exist in these charts. And I could, even though like they have different coordinates, I'm able to inversely map from one chart to another. I'm able to transition to one chart to another. So I could go back to V, and then I could figure out what is the image of that point in a different chart. And I could go take an inverse of it. So there are transitions that are defined that allow me to go from one chart to another. And this is what it looks like. So all I have to do is take the inverse right there and then do a composition of it to figure out what it looks like. So these are called transition functions. Let me give you an example of another manifold. This is something a little bit less abstract. So one object, mathematical object we study a lot in topology is a donut, or also called a torus. And as you can see here, this is a manifold. And this is an example of two-dimensional manifold where you could take an open set V and define basically a chart. So this is a two-dimensional manifold. So now let's go to spacetime, which is an example of a very useful manifold, a four-dimensional manifold. And space-time is a collection of points, and these points, now we're going to look at this in this context of physics. So these are a collection of points called events. And an event, you could consider an example of in space-time an open set. So an open set U in this example is a subset of the space-time or manifold M. And it is a collection of elements, and it has a topology defined on it, standard topology defined on it. And I could define basically a chart that looks like this, which maps from U to R4 in this example. So when I do that, this introduces a set of coordinates, x0, x1, 2, 3. And so you have x, y, z, and then you also have time, which is t. So one observer may define a chart, another observer may define a different chart, for example. They will define the same event. They have the same event, but they're defining different coordinates for it. And so you have another observer which has its own frame of reference and is defining its own chart. And I could go from one coordinates to another using Lorentz transformations. And so this is the basic simple idea or framework of space-time. Whenever you think of space-time in a mathematical point of view, you want to think of it as a four-dimensional manifold. And what I could do is take this idea further and define a metric on it. So I could define like a short shell metric or Kerr metric on it, which is a way to define distance. And so this is the basics of space-time. In further videos, we're going to do a more deep dive on what it is. How do you look at space-time examples of different space-time metrics? And if you want to learn more, I also make videos on coding. You could go to my website, codingwithmohit.com. I also have content on Compose in this channel and Kotlin.